Colleagues. I represent the Samara University. I don't know. You do. So the Samara University is something that we got after the merger between the Samara University and Aerospace University, and the Samara State University, which was sort of classical university. This has provided humanities and so natural science. And etc. And so I work at this University of Samara, and I have very small presentation, very short presentation. I'll talk about the education in this very important sphere as digital microprocessor technology and our view. How we should modernize and change it for the better. So we know that the progress of microprocessor technology is quite fast and very intense. By the same time, so the opportunities for a student just to make into a good specialist very limited. So that's why we cannot borrow all the new things. So then hardware, software, and we need to develop our own. So we need just to have to provide some fundamental knowledge that makes it possible for future students and would-be professionals to be able to work independently. And so we have specialists from software. So this basic foundation, basic knowledge is very important, and we need to provide that kind of knowledge. And so then these specialists should be able to wield so wider so gamut of knowledge, and so this is very useful just to have this excellent, robust background for the students. So there are lots of problems of different kind, and actually, so there are two different approaches exist. If we take big brush strokes, so then the training specialists, as specialists of so the specialists who develop microprocessors, for example, like the previous speaker spoke about. And the second is the training specialist teaching them who do not develop microprocessors and chips, but they apply them. So they just polish them, iron them out, and use them. And so that's why they should be simultaneously programming engineers, developers, because it's exactly what they do. So develop programs. So the main approach for the students, developers, as you say it, so is a basic course. So it's introductory course. So the students, so they learn only the basic facts, and then they move forward, and then they have this some microprocessor, microcontrollers, basic course. And as you can see, this is the list of things that we teach them. And so there are some challenges here as usual. First is those who are familiar with the digital technology, you probably remember how it was. Even they even used the Soviet time. So textbooks, but everything needs to be certainly upgraded and changed. So we're cutting on so some diode hardware. So we removed them because so then elements, components, we decided not to concentrate on them nowhere near to the same extent as we used to do it, because that's not relevant anymore. And so the main nodes, then microprocessor architecture, that's more important. And then certainly we're thinking about our employers, because there are many employers are very conservative. For example, I know some companies they're using that, so then 133 series development, and so very. So I'm not going to talk about the 33rd series, but we cannot abandon it because they are our customers, and that is why we need to offer them what they want to get from us. And then in the last 10 years. So we have added the Please course. So we work with Xilinx company, and they provided to us some tuning boards, and that's very important for students to learn more about digital technology. So they learn because they have the board how to make a simple one, a simple design, more complicated design. So we're trying just to fit it in within that training course, and I think that this important segment is covered. Then this is microprocessors, 8 series processors. So this microprocessors. So there is a thing of the past. There are 32 already. So 8 is very little. 16, 32 are coming processors. But we need to start small, and so the software is quite straightforward, and the student can do it very well, simply using the computer simulation model, and then we learn timers, so stacks, so step by step they learn, and eventually acquiring this necessary knowledge. Then we talk about 16 and 32 microcontrollers, and so they're getting more and more complicated. So the language is C, C++. And so then we do it more and more complicated for 16, and so then we use the 430 family, and so this is the CC. So you compile, this look, study, and etc. So encouraging them. And so then the students learn what the compiler is and how it works. And let me speed up a little bit. Yes, so then we keep. So let's talk about what if you have anything new. So leveling of data and other things. Then we have so signal processors, digital processors, etc. And then there's a special course of digital algorithms. So how to do this? Algorithms or something else. Several experiments have been made, so either parallel or first processors, and meaning what? So the classification, processor specifics, etc. So we can do digital filter, maybe, and then different methods, etc. Algorithms. Yes, then maps. So it's easy, certainly, just to for everyone to so then indication, all these things, yeah, and power, etc. And then you can see how it works. Then the students do it themselves already. Then interface of data transmission. Interface is something that so the hardware is not made out of them. Then you can see this CAN link, USB, Ethernet, etc. So the students do that. So there are lots of tuning boards. So very interesting things that's for the students to play, to learn more, to study, and to see how this things work. And then for bachelors, so we start about the so testing. So then so the interference protection, and then BGA, and then the other boxes very difficult so to get to them. And that's why we need to develop the system from the very beginning to make it in a robust manner, to be able to test so both the boards and all the links, all the connections, and to monitor. And then interference protection, etc. So different protection from different electronic static interferences. So as the speed grows, so the chips are getting less and less protected, and so then the protection goes down. And the trend is that as developers say, that's to shift the responsibility of interference problems so onto the developers of chips, because it's their responsibility, because it's their hardware. So quality should be observed, plus interference protection from all electronic devices. And then we do have practical exercises. So do we have developing of digital devices on the basis of PLEASE Spartan 6, then software development for 8-digit microcontrollers, development of software for 16-digit microcontrollers, etc. So these are the practical on hands experience. The students get this kind of experience. So then lab studies are very important, and so then there's a great deal of interest in practical studies, on hands experience. And so we do have some candidates who help to develop. We have developed the course, Russian-made course, high performance Russian-made course. Then we do have remote learning, remote teaching, and so not only our ministry, that's the world trend. So then independent training. So because the resource is available, it's on the internet, it's so much more available than used to be 20 years ago. And so we do have all the steps of training components in the Noodle system. And so then they can get access so through a special system of passwords, and so they learn by themselves out of their homes. And so they, from the very beginning, so all our students have all the materials, so all the presentations are on the web. Yes, all the textbooks and tests and files, everything is in there. So then, and so for example, so then this module of MSP for 30 peripheral modules, MSP for 30, so I can easily control how they do it. And that's the way this this quiz looks like, and I know just which student and when. So they what they did actually, so what kind of progress they made, and we can always watch his or her progress and then control the way they are taught. Okay, my time is up. If you any more questions, I'll be happy to discuss, and so your opinion will be very valuable. So what would you like to to see, and what kind of knowledge you want our students to have when you hire them as employers. Thank you. This question about and theory, theory. So when you use practice and theory, so you talked about both, and this is good. And the question, so how do you design your learning process? For example, validation, testing, so then simulation, Octave, MATLAB, so FPGA language. So how do you cover it all? So then there's no special chapter so about testing. We don't have it, especially at the beginning. So the bachelor's degree for the bachelor. So then the master's degree, we do have special courses related to quality. So that study the foundation of this issue. So for example, we have so the functional testing, and then we have. So see this, it works. So the diodes glow, everything works, the system ticks. But if we talk about software, then we have our own compiler. So then the tuning, fine tuning, optimization, harmonization issues, they do that too. But this is quite challenging. It's quite convoluted. But on the other hand, so if we so then the system is much faster now, and the big storage capabilities. And it turns out that it's much more valuable when a developer quickly writes a code that will be functioning, operating, and do what it's supposed to do. But maybe it will take more memory then and take more resources. And this is more valuable rather than that it will take him another 2 months, and iron it out and saves 2 kilobytes. But about FPGA, so I work with Xilinx, ICE, so they give us a chance to see the stability and speed and efficiency. But the special verification, validation is not done at the first course. Thank you. And so now, just while the next speaker is getting ready, and so if all the students have this knowledge, original, this is great, because usually to our company we have students and we are developers, and so in St. Petersburg, it's good if they're so capable when they graduate. Correct me if I'm wrong. That learning programming, learning development is done on a specific course, right? They don't know any development algorithms. They don't know any industrial development. They don't know what Git is, right? So they don't know things that they teach at the university. So they're just radio engineers, right? No, this is it has to do with our standards. So there's a special department in our university. It's IT department, and they have a basic course that gives the basics of the digital technology. And it's a red engineers training course. And the rest part of it is development effort. So they explain how to develop program, how to do the programming. But this is the basic one, and it's part of this radio engineering course, and then some network information technology. So we don't teach them software engineering, and those who do the software engineering, so they don't study the hardware engineering, and that's why. So these are the two different things, and we're trying just to find a happy medium between the two. So this is correct, because we take programs and Novosibirsk actually. We take these programs and see how they So they changed the code. So then registers with the help of compiler downloaded, and so the speed went up. So then efficiency went up. Maybe this joint effort, and then this divisioning between software engineering, hardware engineering, this is logical. Okay, please give our speaker.